Hello students, welcome to my YouTube channel Get Metallurgy MT. In today's video, we are going to discuss important concept from thermodynamics, the Ellingham diagram, that is Ellingham diagram. And later we will solve the GATE previous year metallurgy question from GATE 2015. This question is from GATE Metallurgy 2008. This question is from GATE 2017. This question is from GATE 2005. This question is from GATE 2011. And last question we are going to see from GATE 2013. So now first of all we will understand the concept of an Ellingham diagram. So let's get started in the video. Ellingham diagram is a graph that plots the gives free energy delta G naught for the formation of oxides as a function of temperature through per mole of O2. And this Ellingham diagram is governed by formula delta G naught equals to delta H naught minus T delta S. Delta G naught is gives free energy, delta H naught is change in enthalpy, T is the temperature, and delta S naught is change in entropy. If delta G naught is less than 0, then reaction said to be thermodynamically stable. Delta G naught for the formation of per mole of oxygen. On the other side we have temperature. The above equation is similar to y equal to c plus xm, that is y equal to mx plus c, where c where c delta h is intercept, where m, that is minus delta s naught, is slope. So the graph would be something like this. This is delta h, delta s is the slope. Now we will insert Ellingham diagram, which is this one. In this diagram we can see that there is a temperature axis here and there is delta G axis here in the y axis, and these graphs are linear graphs which is plotted as according to this formula. From this graph we will note down the important points, that is, and this is one of the key concept of this graph. Lower the line on the diagram, more stable the oxide. That means if some oxide forms lower in the diagram and some oxide forms upper in the diagram, then the oxide that is formed lower in the diagram is more stable than upper one, less stable. So suppose that we have two lines. Suppose that this is T1 temperature. According to the above statement, for temperature T less than T1, lower in the line is this green part. So this is more stable. And for temperature greater than T1, red line is lower in the diagram. So this part is more stable. Means oxide of this will be more stable. Here oxide of this will be more stable. Now we will understand this with the help of example from the Ellingham diagram. Suppose that we have taken CO2 line formation where C plus O2 give rise to CO2, and another line, that is where in this case 2C plus O2 give rise to 2CO. In this case we will see that, and this temperature is around 800 degrees Celsius. Now when the temperature is less than 800 degrees Celsius, we will see that lower line is more stable here, means the product CO2 is more stable, and for temperature greater than 800, this blue line is more stable. So CO product will be more stable. So we can write for this, we can write this reaction 2CO plus O2 give rise to CO2. That means, so for this case, out of the CO and CO2, CO2 is formed because CO2 is more stable here. In the second reason, we can write, for the second case, we can write CO2 equals to CO plus O2. So in this case, we can see CO is more stable than CO2. That's why CO is formed. Now there is one more concept that is frequently asked in the examination, that is why the formation of CO2 line is horizontal. For this question, we can write the reaction as carbon plus O2 give rise to CO2 gaseous. This is solid phase. As in this reaction, 1 mole of oxygen combines to form 1 mole of CO2, and both are in the gaseous form. So the entropy change in this case is negligible, that is delta S is almost 0. That's why slope in this case is 0, that is m equals to 0. That's why the line is horizontal. Similarly, one more question is asked, why the formation of CO2 from carbon is going downward. Similarly, we can say that the reaction for this is 2 carbon plus O2 give rise to 2 CO2 gaseous. In this case, we can see that 1 mole of oxygen combines to form 2 mole of CO2. Now in this case, the entropy is increasing. That means delta S in this case is positive. When we will substitute this value in the relation delta G equals to delta H minus T delta S, we can see that when we will substitute this value delta S positive, overall we can see that delta S term remains negative, that is m is negative. So the slope in this case is negative. So now we have understood all the concept related to Ellingham diagram. Now we will solve the previous year question. So the first question here is from GATE 2005. According to the question, in Ellingham diagram, the slope of the line represents. Just now we have seen the formula delta G naught equal to delta H naught minus T delta S naught. And we have drawn the graph as y equal to C minus xm. So from this corollary we can see that the slope is negative in this case. M is negative of delta S naught. So option B is correct for this question. Moving to the next question. This question is from GATE 2015. In an Ellingham diagram, the standard free energy change delta G naught for the oxidation reaction of a metal M is given by Xm solid plus oxygen gas give rise to Mx O2 solid is plotted as a function of temperature. The slope of the line is positive because in one of the concepts we have seen that 1 mole of gas give rise to 0 mole of gas. So in this case entropy is decreasing. Therefore change in entropy will be negative. Similarly, in the formula we can see that delta G equals to delta H minus T delta S. From here the slope m equals to minus delta S, and in this case the slope is also negative here, change is also negative. So we will say that overall the slope will become positive. This is all because the delta S here is negative, means slope is negative. So option B is correct for this question. Now moving to the next question. This question is from GATE 2017. Now according to the question, T1 and T2 are the melting points of pure metal A and pure stoichiometric oxide AO2 respectively. T1 is less than T2. The stoichiometric metal oxidation, a solid plus oxygen gas give rise to AO2 solid, is in equilibrium at 1 atmospheric pressure at temperature less than T1. This is for temperature less than T1. If the temperature increases, which is schematic represents the correct standard free energy change versus temperature plot. For temperature less than T1, we can see that 1 mole of O2 gases give rise to 0 mole of gaseous phase. So, in this case, the entropy delta S is decreasing. So, from the formula delta G naught equal to delta H naught minus T delta S naught, we will see that slope M here is negative, that is M is minus delta S naught. Therefore, and delta S, that is change in entropy for this reaction, is also decreasing. So, the change will be negative. So, for this reaction, overall the slope will be positive. Therefore, all the four options are with increasing slope. Increasing slope. Now, for temperature between T1 to T2, as according to the reaction, the A phase metal is in the liquid state because it already crosses the melting point of A at T1. So that is in liquid state plus oxygen gaseous give rise to AO2, that is still in the solid phase. Therefore, from this reaction, similar to the previous one, we can see that there is more entropy in the LHS and there is no entropy in the RHS. Similarly, like the previous case also, the slope would be positive because overall the entropy is decreasing. But the value of delta S in this case and from the previous case, we will see that the delta S is more positive in the second case because there is liquid and gaseous phase changes to solid. As we know that randomness of liquid is more than solid, so the entropy value here will be more. Therefore, we can say that the slope is more positive, so slope should be increasing further. In the A case, we can see that slope is decreasing, so we are left with three options. But in D case, we can also see that the entropy value is decreasing with respect to the previous case, but it should increase because the delta S value is more. So this is also wrong. So we are left with B and C. Now for the third case, when the temperature T is greater than T2. For this temperature, the reaction will be A liquid plus O2 gaseous give rise to AO2. This will be in the liquid phase. AO2 already crosses the melting point temperature, and that is temperature is greater than T2. So now when is so similar like the previous two cases, we can again see that the entropy will decrease. So delta S would be decreasing because liquid plus gases give rise to liquid. So entropy will be decreasing here. Similar like the first case, the slope value will be less as compared to the second value. So overall delta S is for the third case, that is T temperature greater than T2 is less than change in entropy for temperature in between T1 to T2. So the slope is decreasing from second case to third case. Here it's decreasing value from second case to third case, and from second to third in this case is increasing. Option C is correct for this question. Now we will move to the next question. This is gate question from 2008. In Ellingham diagram, C giving to CO line intersect with M giving to MO line at temperature T1 and N giving to NO line at temperature T2. M and N are two metals where T2 is greater than T1. The correct among the following is. So first of all we will construct a Ellingham diagram for this question. As we know that C giving to CO line is a horizontal line, so this will be like this, and metal giving to metal oxide, for both of these M and N it will be a positive slope. First one it will intersect at temperature T1, second one it will intersect at temperature T2, and it is given that T1 is less than T2. Now we can divide this in three regions, that is region 1, region 2 and region 3. C giving to CO, for the region 1 we can say that this region is more stable. For region 2 this is most stable, and for region 3 this is most stable. That is temperature less than T1, we can say that MO is most stable. That is, in case of region 1, that is temperature less than T1, carbon do not have the ability to form carbon monoxide because carbon metal oxide MO is more stable, not carbon monoxide. So carbon cannot reduce MO or NO or both. Reason 2, when the temperature is between T1 to T2. In this case, carbon can reduce only if it has the ability to form carbon monoxide. So, in this case, carbon monoxide is more stable with respect to MO. So, it can reduce MO, but it cannot reduce NO because NO is more stable oxide than carbon monoxide. And reason 3, temperature greater than T2. Again, if carbon wants to reduce metal oxide, it should have the capability to form carbon monoxide over all other oxide. So we can clearly see from the graph that carbon monoxide is the most stable phase. So for this case, carbon can reduce both MO and NO. So now we will check the options. For temperature T greater than T2 means third case, carbon will reduce both MO and NO at temperature. So this is correct. Second statement, for temperatures between T1 to T2, that is region 2, carbon can reduce both MO and NO. No, this is wrong because carbon cannot reduce NO. Option 3, carbon will reduce both MO and NO at temperature T less than T1. So this is the first reason. In this case, carbon can't reduce both or either of one. So this is also wrong. For the reason 2, temperature between T1 and T2, here carbon will reduce MO but not NO. Carbon will reduce MO but not NO. So this is correct statement. T is carbon will reduce NO but not MO. So carbon will reduce NO. So this is wrong. So for this question, clearly P and S is correct. So option A is correct. Now moving to the next question. This question is from GATE 2013. In Ellingham diagram for oxides, CCO line cuts MMO lines at temperature T1, and so this is C, CO line cuts the line MMO. Suppose that this is MMO at temperature T1 and M dash O line at temperature T2, which is higher temperature. So M dash to M dash O at higher temperature T2. So this is T2 temperature. At a temperature greater than T1 and less than T2, the carbon can reduce. So they are talking about this region. For temperature less than T2 but greater than T1 in this region. Clearly we can see that M dash O line is lower. So this is most stable. Means and MMO line is at top. So and CCO line is at in between. So carbon can reduce only one of them. So both option is gone. Neither option is also gone. Now if carbon wants to reduce any other metal oxides, it should have the ability to form carbon monoxide. Means this should be the stable phase. Then only carbon can reduce. In this case we can see that for only one case carbon monoxide is more stable, that is for MMO. So carbon can reduce MMO but not, rather M-O can reduce carbon monoxide because M-O is more stable. So option E is correct here, where carbon can reduce only MO. Moving to the next question. This question is from GATE 2011. Aluminium is not commercially produced by carbothermic reduction, primarily because. So now we will insert Ellingham diagram here. In this Ellingham diagram we can see that aluminium is here and carbon or carbon monoxide is here. To produce aluminium through carbothermic reaction, carbon has to reduce aluminium oxide. But in this case we can see that aluminium oxide is lower in the Ellingham diagram. That means aluminium oxide, that is alumina, is more stable than carbon monoxide or carbon dioxide. So carbon can't reduce alumina, that is Al2O3. Also, due to the high stability here, alumina melting point is around 2100 degrees Celsius, which is too high. So alumina line is too low in the Ellingham diagram, needs excessively high temperature. So option E is true here. Option C is also true because it does not vaporizes at reasonable temperature. Also, for the statement A, aluminium metal dissolved is excessively high because alumina is very high stability. That's why there is high tendency or affinity for oxygen. This is also one of the reason it can't be reduced through carbothermic reduction. So option E is also correct. Only not correct option here is option B. So for this question Option B is correct. Hopefully you guys have understood all the concepts and the previous year question we have gone through, and you are ready now to tackle any problem from Ellingham diagram. Thank you so much for watching the video.